problem that we were working last class period. So let's jump in here, and any questions on that schedule, throw those in the chat or turn on your mic there. Are there any questions about that schedule? FBD number 14, FBD number 16, anything like that? So number 4 will start, good question, Chloe. Number 4 will start tomorrow, and I'll get it all set up on Canvas, and it'll be ready to go tomorrow for recitations. And our next exam is the 16th. Yep. And you can go back and look at the semester schedule. It shows the next exam on there. And we will post, I'll get the practice exam posted sometime this week with the list of all the topics and all that stuff so we know. Okay, so we were working on this problem last time, remember, where they were asking us to find the force in this hydraulic cylinder from B to C, and the pin there, the forces in the pin at A as well. And so we had talked about a couple of different things. First, we went through our steps, and the steps over here in purple were to identify all the rigid objects. And so we did that over here on the left side of the screen, and we identified the rigid objects and then the type that they are. Are they multi-force? Are they two-force member? And then we considered the FBDs of each of those rigid objects. So that basically provides a list of all the possible free body diagrams. And then we said, well, let's pick an FBD out of that list. Let's pick one that has knowns and not too many unknowns. And so then we said, oh, okay, well, ABGE, that was the only one that had known values. It had the 125 and the 600, and we've got the FBD of ABGE drawn here. And so we had left off on Friday by saying, well, what equation are we going to use first? Are we going to do sum of forces in the X? And then we looked at that and we said, oh, actually, how many unknowns are we going to have in there? We're going to have 2 unknowns. And then we said, oh, okay, well, what about sum of forces in the Y? And we said, oh, well, we're also going to have 2 unknowns in that one. And then we said, well, is there an equation that would just be one unknown? They would only have one unknown, because we don't want to solve systems of equations if we can find one equation with one unknown and then go to the next equation with one unknown and the next equation. Then it's just easier for us to do that math. And so we said, if we sum moments about point A, it actually will not include, that equation will not include AX or AY, because AX and AY do not cause a moment about point A. So by picking points where there's 2 forces that occur, 2 unknowns, we exclude those from our equation. And now we're left with just the only unknown in our sum of moment about A equation is going to be FBC. FBC is at a 40-degree angle, and so what do we do when we have a force at an angle? Well, we break it up into components. And so we could have this X component right here. That would be FBC times the, let's see, our 40 degrees would be a cosine of 40. And then our Y component would be right there. And that one would be FBC times the sine of 40 degrees. Also want to remind everyone that we did not have to pick a direction, or we did not have to worry about what direction we picked on FBC. We could have drawn FBC up and to the right. We could have drawn FBC down and to the left like we did. Same with AX and AY. We can draw them whatever direction we want to. Now, one thing that is good practice is for us to draw those forces on top of where the rigid object used to be, right? Isn't this, the force in B to C is, if we go up to this picture up here, there's our rigid object for B to C. The F from B to C is really the force from B to C that's acting on our rigid object that we pick for the FBD. So that FBC is the force of BC acting onto ABGE. And so let's draw it on top of where that rigid object used to be. That rigid object used to be down and to the left. And so notice I drew it down there. So regardless of what direction I draw it on top of where that physical thing that we're replacing used to live. It doesn't, you don't have to do it mathematically. It's exactly the same. But as we move through statics, it'll make more sense when we do that. Okay. So now let's look at some of the moments about a equation. We should be really good at doing this now. We started back in like lecture number 7, just being able to take a moment about a spot. Well, now we're using moments to find unknowns. And so if we look at our sum of moments about point A, we've got our counterclockwise is positive. The 125 will be negative, and it's going to be times a distance of what? Let me ask somebody from the front row. So I've already figured out that it's negative because it's going to be going clockwise here. But what's my distance to that point there? Is Anthony Garcia here, or Garcia?
Would it be 4 feet?
Yeah, 4 feet, exactly. So 4 times 4 feet, right? Because we got 1 foot plus another 3 feet. And then the 600 is also going to cause a negative rotation times a distance, a total there of 9 feet when I add up all of those. So those are all of our perpendicular distances. Now we can do FBC. So we're going to let's do FBC cosine of 40. And so that's the x component. Is that going to cause a negative or a positive rotation about point A? Alfred Franco, what do you think? Negative or positive? So I'll go down the line here then. Hannah Garland.
I think clockwise, so would that be negative?
It will be clockwise and negative, absolutely. And then our distance is the vertical distance right here. It's this 1 foot right there, vertical distance times 1 foot right there. And then we're going to have the y component, FBC, times the sine of 40. And let's see, what is that going to do? Oh, that's also going to be a negative as well. That's also going to cause about point A. It'll cause clockwise. And its moment arm is also 1 foot, but that's a horizontal 1 foot distance right there. So that would be that 1 foot horizontally right there. Okay, so now I've done everything, right? Everything that causes a moment, and I have not done any algebra, so the only thing that goes on the right-hand side of my equation is 0, so equal 0. Now I can start doing algebra and start solving for this. Actually, when I do this, I'm going to find that FBC is equal to a minus 4,188 pounds. So I got a negative number, and you see I got negative. Every single term in this has a negative, doesn't it? And so when I solve for it, I'm going to get a negative number. Well, that means it just goes the opposite direction as drawn. I do not want to go back and change it. I picked that direction. If I went back and changed it, well, I'd have to change the signs on my equation that we just did. And that gets us into this kind of like infinite loop. Not an infinite loop, but it gets us into a loop where we're like going back and changing our FBD. Once we pick that FBD, we just stick with that FBD there and don't even worry about it anymore. But let's look at how we handle the negative sign when we do that. There's a couple of different ways to do it. What I like to do is I like to ignore the fact that I got a negative, and I'm just going to use my picture. So when we go into our next equation, and sum of force in the x or y would work, they both only have one unknown. I'm going to go ahead and go into sum of force in the x. That has an ax going to the right. My FBC, the way it's drawn in my FBD, is that going to be a negative or a positive there? Eilish, what do you think? Negative or positive for my x component of FBC, which is FBC times the cosine of 40?
Would it be negative?
But based on my picture, absolutely, it would be a negative right there. So minus FBC cosine of 40, that's everything in the x direction. So I just say, well, that has to be equal to 0. Now, the way I handle my negative number, instead of trying to like think about, well, actually, it's actually going in the opposite direction on my picture because we found a negative 4,188. What I do is I just leave it as is, and I go, well, it's minus, and then I'm just going to plug in a minus 4,188 times the cosine of 40 is equal to 0. So actually, it changes it to be positive, right? Because it will have a positive x component. But actually, when I do my ax here, I'm going to find that ax is negative 3,210 pounds. So again, I found another one. It goes opposite, which is totally fine. I do not have to get the right, or I don't even want to call it the right direction. I don't have to get the sign correct direction on any of my forces that I draw in my FBD. So I get a negative 3,210 for AX. When I sum forces and the Y is equal to 0, I'm going to end up with an AY is going up. My FBC, the way it's drawn, would be a minus FBC times the sine of 40. And then we also have a minus 125 and a minus 600 is equal to 0. And so when I plug in for FBC, we're going to plug in a minus 4188 in that spot right there, right? I plug in a negative number. I'm going to find my AY actually needs to be minus 1967 pounds. So it also needs to go opposite the way that we drew it as well. So they're all going opposite direction, but it doesn't matter. Still find exactly the same thing as if I had drawn them all in the other direction right there. I also want to point out here the magnitude of the forces. FBC, there's 4,000 pounds in FBC to support 125 pounds and 600 pounds. So imagine in a real piece of machinery like this, because of those distances out to the 600 pound, we end up carrying much larger forces in those hydraulic cylinders and at those pins than the actual load that we're carrying. Also, another cool thing though is that we are able now to calculate. What happened to my steps there? They got all combobulated. But we're able to calculate the forces in these types of systems now. And actually we'll continue doing that as we go through this semester and continue advancing on our abilities to analyze things like this. My steps, I don't know why they got all kind of moved around there. Must have been when I was shifting things. But remember, we can follow those steps for all of our problems in statics. ID the rigid objects, consider an FBD of each rigid object, pick one with knowns and not too many unknowns. And then our fourth step was sum of force in the X, Y, and some of the moments. And we think about all those as just identifying all of our options and then picking, going through those options. There's nothing wrong with just saying, what about an FBD of this? What about an FBD of this? What about an FBD of this? And then also going through our equilibrium equations and saying, well, what about this equation? How many unknowns? What about this equation? What about this equation? There really is no magic when we're solving these problems. It's not like, oh, because of this, I recognize, now that means I'm going to use this equation first. I don't approach statics like that. I don't approach problems like that. You approach problems by identifying all the options, and then once you have all the options, going through them and picking the one that is the one that's going to work. I see a question here. Since we find the direction of the forces while we calculate it, does that mean that the directions we put the force arrows in the FBD homework last night don't matter? Yes, they don't matter at all. Absolutely. Now, a cable can only resist tension. A roller will never resist something from lifting off of a surface. But even though those only will work in one direction, if the system is a real system, the math will still tell you it needs to go in the opposite direction. So you technically never have to get them going in the sign correct direction. Okay, any other questions on this? Okay, we're going to get into 3D stuff here in a second, but I wanted to bring up one more thing, or overturning. And we looked at overturning when we first talked about moments here, and we watched this crane fall into the water when they were trying to pull out this car. So an overturning problem is 2D rigid body equilibrium as well. And for example, to figure out whether or not this crane here on the Mines campus, they were loading some equipment onto the roof in the Green Center when they were doing construction on it. Notice these outriggers sticking out way out here and touching the ground. Even the wheels on this thing are actually off the ground right there when they've got this load up here. So they need to make sure that they're not going to overturn. Or what about this one right here in front of Marcus? And actually, remember the cantilever example we did last time where we said, there's this cantilever sticking out over, this is the cantilever we were looking at over Marcus. Well, they were doing some work on the panels underneath there, and they have these people out here, and don't you think this could go overturning that way and fall and go crashing through all this glass here? That would be really bad. Actually, a lot of this machinery has warning sensors on there that start beeping, and they prevent you from getting to that point where you do have that overturning, which there's that crane that we talked about, that we looked at in this overturning stuff. And then another example to illustrate one of the key concepts for us to be able to calculate overturning is I have this mini excavator, and this person has this big rock right here, and they've got, notice the track is mostly in contact with the ground right there in that picture. And then as this mini excavator is lowering that rock into this hole right here, look what happens right back here. We see we're starting to lose contact with the ground right there. And then some of these operators get a little bit crazy. This person knew they were going to catch themselves, but look at what happened, right? When overturning occurs, the normal force is going to be all the way at the tip right there of that spot. And so if we were to look at a problem like this, and we're going to go through this kind of quickly here, we'll talk about it a little bit more as we move through the semester, but we would do an FBD of the whole thing, because the whole thing is what's going to overturn. The whole thing moves together. And so if we have this weight out here, and we have a normal force here at A and a normal force here at B, if this is going to overturn, we have a weight here at C, there's also a weight here at point B. If this is going to overturn, what do we think the normal force at B is going to be equal to when we're right on the verge of overturning? Can we set a specific value for that? Anyone? Anybody know what would the normal force at B, thinking back to that excavator, what happened when they did overturn? Where did all those normal forces go? 0. Yeah, normal force at B would be equal to 0 when we're on the verge of overturning. So we have to know that. That's our first key thing when we're doing overturning problems, is knowing that the normal force is equal to, at that point, at whatever point, whatever point is going to come off the ground, and we have to think about that physically as to what would happen if this did tip over. The normal force, when we set it equal to 0, we're saying we're on the verge of overturning. Now, it gets pretty scary if you get down to, like, what if the normal force at B was like 100 pounds? Now you're getting close, right? As you increase this W out here, you're getting close to being on the verge. And then what if it gets down to 10 pounds? You're getting even closer. And then once it gets to 0, that's when we're now on this verge of overturning and having this crane tip over. Now we could solve this now. Once we set normal to B equal to 0, we can solve this by summing moments at our pivot point, which would be A, and we can actually solve for whatever they're asking us to solve for in these problems. Question? Okay. Okay, any questions about that? Okay, let's move into doing our free body diagrams in 3D. Just like we did for 2D, we had one lecture where we just talked about free body diagrams, and it was more conceptual. We're going to do the same thing. And then on Wednesday, we will go in and we'll start solving these problems. Also, like I mentioned before, handwritten homework number 7 due this Friday also includes the FBDs for FBD number 16. Our learning objectives are essentially the same thing as they were for 2D rigid body. The only thing that's different is it's table 5.2 now instead of table 5.1. But we need to be able to draw all the correct support reactions forces and moments for all the types of connections listed in table 5.2 of the text. The FBD should be such that the entire problem can be solved without looking back at the original problem statement. And we also, just like before, determine the number of unknowns for any given FBD. That's really key with our process for identifying, right? Is to pick an FBD with knowns and not too many unknowns. So we got to be able to figure out the number of unknowns. Still have two force and multi-force members. We determine them exactly the same way. And then we will consider more things about whether a system is stable or unstable if a system is determinate or indeterminate. I showed you this picture last time. This is that I was going to call it a backhoe. It's not a backhoe. This is a tandem dump truck that carries about anywhere from probably 10 to 12 tons worth of gravel in there. And so imagine how much force is going to be in that hydraulic cylinder when it's lifting that bed up to dump those 24,000 pounds of gravel right there. But this is a two-force member. Now, we can simplify this down to two dimensions. How about these ones, though, on the rec center? If it only has two locations of forces, it is still going to be a two-force member. So, for example, this one right here, it only has two locations of forces. Now, one thing we're not sure about is whether or not these resist a moment, because remember, if there's a moment applied or a fixed support, a moment from a fixed support, then it's no longer a two-force member. To get a moment connection, you really have to beef it up like this one down here. This is probably a moment connection, but let's assume that if it's a connection, they're actually mostly going to behave as a connection that does not carry any moment. So that's a two-force member. This right here is a two-force member. This is a two-force. This is a two-force. Up here at the very top of this is a multi-force though, and we can tell because it's got 1, 2, 3, and then 4, 5. So it's got lots of places where those forces occur. So same way that we identify things, whether it's a two-force or multi-force, if it only has two locations, it's a two-force member and no moments. If it has a moment or if it has more than two locations, then it's a multi-force. Here's a picture of a concrete pump crane that is bringing in concrete for the parking garage back when they started placing concrete. Every single hydraulic cylinder on this pump truck right here is a two-force member. The other ones, the frame part of that, the darker blue, those are all multi-force members on there. So lots of stuff in practice, lots of real-world applications for these two-force and multi-force members. Here's the first 2 of 5, just like you saw in FBD number 14. We are asked to draw a free body diagram of the shaft assembly, which is supported by a thrust bearing at A, a journal bearing at B, and the short link from D to C. So short link, anytime we see that word short link, that tells us that is a two-force member in there. So we know that the line of action has to go between those two locations where those forces occur. So we would draw an F from C to D on that one right there. Now we're going to talk about what a bearing is and what kind of forces those have. Again, going back to our more of a logical approach where we just ask ourselves, what is it allowing to happen? What is it preventing from happening? Also a note at the top here, neglect the weight of the members unless they're specified. Somebody had a really good question about that a few lectures ago. Unless we tell you the weight, just assume that they're 0. We do tell you the weight on a couple of these though. Now that we are in 3D, we actually can see problems with 6 unknowns. So we went from 3 unknowns to 6 unknowns because we added an equation for force in the z direction, but we also added 2 moment equations because now we're not only summing moment about a point, we're summing it about an axis. So we can have 6 equations with 6 unknowns, but again, we really want to figure out what equations to use first, second, and third, etc., so that we don't have like this huge system of equations. Ultimately, I still want to find one equation with 1 unknown. And even though we're in 3D, we're still going to have supports with only 1 unknown force, like a cable. It might be at a three-dimensional line of action, right? It might be an X, Y, and Z component, but it's still only one unknown because we'll express it as the magnitude times the unit vector like we've seen in the past. Or how about a smooth surface support? A smooth surface support, well, it's only going to be perpendicular to that surface regardless of whether or not the surface is at a three-dimensional angle, right? If it's at a three-dimensional angle, well, then the force will be perpendicular to whatever that surface looks like. A roller, same thing as a smooth support here. So rollers, we saw all these in 2D as well, right? Rollers, smooth support, same idea in 3D. A ball and socket, there's a good example of a 3D type of connection and support here. And look at that ball and socket joint, that picture right there. Again, thinking about what is allowed to happen and what is prevented from happening. Well, I think a ball and socket is allowed to rotate, right, in any direction. It's allowed to rotate on the x-axis, the y-axis, and the z-axis. So we don't see in our picture there from the textbook, from table 5.2, what do we see? We don't see any moments, but it's preventing translation, right? Do you think you could take this ball and move it this way? No. Do you think you could take this ball and move it this way? No. This ball and move it this way? No, right? So we have a force in the things that that physical object prevents. Also notice when they draw this over here, they remove they take the socket off, right? They just have the ball there. So remember to remove those supports when you draw the FBD. So that one has three unknowns. How about a single smooth pin? What is this allowing to happen? Well, this one allows rotation, but only about one axis now. And so we see in our picture down here, we have all three forces, and now we have two moments. We have a moment about the Z and the Y, but no moment on the X because it's allowed to rotate on that X direction. So again, what is allowed and what is prevented from happening? If it's allowed to happen, don't put a reaction force or moment there. Washington Street Bridge is a really nice example of a single smooth pin. And I need to take a better picture of this. I needed to take a class 2 on cinematography, I think also. But here's this pin. This pin is sitting right in here. And so actually that connection allows these to rotate back and forth here. But it's the connection. It's all these cables up at the top here that prevent it from happening. But we now know what forces and moments are going to go there, right? It'd have all forces and all the moments except for the one along that pin where it's allowed to rotate. Okay, now how about a journal bearing? A journal bearing is also something that allows rotation on one axis. So we have, and it's actually made for things to rotate along that axis. So we have this axis right here where it's allowed to rotate on. And so we don't see any moment there, but actually we see a moment on the other two axes and we see forces. Now, the difference between a journal bearing and a thrust bearing is, I like to remember this thrust means we have an extra force. If you compare these two, notice that the thrust bearing, we've got this force here in the Y direction. While the journal bearing, there is no force in the Y direction. So they look exactly the same. We will have to tell you which one's a journal bearing and which one is a thrust bearing in the problem statement. But once we tell you that, you need to know what moment and forces occur. Here's some real world examples of a thrust bearing. This thing is really beefed up to carry this force in that direction along the length of the shaft there. This one right here, while I probably couldn't grab onto this and pull it out, it is not really made to prevent a large force in that direction. So there is no force. But again, thinking about this just as a real world object, it allows rotation on one axis, but it doesn't allow rotation on the other axes there. Okay, we can also see things with square shafts. Here's a single journal bearing with a square shaft, and then I'm showing the single journal bearing again so we can compare them. if a square shaft is going through a square hole, well, we're going to have a moment reaction. And so now we do see a moment along the length of that shaft. Still no force because it's a journal bearing, so no Fy in that case right there. But comparing it back to our journal bearing, what do we see? There's no My down in this one. There's also no Fy in this one as well, right? But it's just the difference between the square shaft and the journal bearing is the My there. How about a hinge? These are like hinges that we see on all of our doors around campus or in our rooms or, wherever. And so what is it allowing to happen? What is prevented from happening? Well, it's definitely allowed to rotate on this axis right here. And so we don't see any moment over here, but we see translation is fixed in all three directions. And it's not allowed to rotate on the Z or the X axis there either. Okay, kind of going through this stuff quickly, but again, let's think about this more conceptually and asking ourselves what's allowed to happen, what's not allowed to happen. And so in this one, in a fixed support, just like we had in 2D, this is going to have all the reactions. It's not allowed to rotate on any axis, and it's not allowed to translate in any direction either. And so we see 6 unknowns if we have a fixed support. Okay, now something happens though when we're in 3D because of stability. Something happens when we have a thrust bearing or a journal bearing, but there's more than one location where a rigid object is supported. This is a class example. This is up on Canvas under the supplementary problems. And if we have a thrust bearing, so they tell us, okay, there's a thrust bearing here at point A, and there's a journal bearing over here at point B. Well, we look and we say, oh, well, thrust bearing we know is going to include 3 forces and an MZ and an MX. And we say, oh, well, a journal bearing will include the 2 forces and an MX and an MZ. Well, if we were trying to solve this, how many unknowns would we have? We have 5 here, and we have 4 here. So if we were drawing an FBD of this crankshaft right here, we would have a total of 9 unknowns. But we only have 6 equations. So we can't solve that. However, something really unique happens when we have a rigid object. If this thing behaves perfectly rigid, which we assume everything in statics is perfectly rigid, if this is perfectly rigid, the moments go away. So when we draw our FBD, it should look like this. It should not include this MZ or this MX or this MX or this MZ. So if you count the number of unknowns, if you count, you can write this down, more than 6 unknowns, all the moments go away. All the M's go away. We do not include them when we draw our FBD. Now, the reason is because, let's think about this as an A. Let's say my hand right here is point A. And this over here is point B. And I've got this force down in the middle. Now, I can hold this thing up at point A if I resist a moment. If I have a moment resistance, that system would be stable. But now as soon as I apply another support over here, I don't need to have a moment reaction anymore at point A. So this B, if we think about this, right, there was originally an MX over here. There was this MX right here. But I don't need that MX because BZ prevents rotation on, or rotation about the x-axis. And so I don't need those moments anymore for stability. So the easiest, what I've written down here, and I'm going to box it in, but this is the easy approach. If you count more than 6 unknowns, all the moments go away. The explanation is because it's a rigid object and the support reactions preclude the need for those moments to occur. So, for example, this is another supplementary example problem. We have this vertical force acts on the crankshaft. Determine the horizontal equilibrium force P that must be applied to the handle and the XYZ components of force at the smooth journal bearing A and the thrust bearing B. The bearings are properly aligned and exert only force reactions on the shaft. So we assume any kind of bearing we have is properly aligned. It does not mean they have to be parallel to each other. It could be perpendicular. They're just properly aligned. But that's it. That's the key right there. They exert only force reactions on the shaft. So if we draw our FBD of this, it would include, because A is a journal bearing, only an AX and an AZ. And B is a thrust bearing, so only a BX, a BY, and a BZ. Notice that there's no M's on there. There could be, right? If I didn't have a total of 9 unknowns to start with, then I would include the moments. If I have 6 unknowns, I would include the moments. And you can't pick and choose. You can't be like, oh, I'll include some moments and not include other moments to get down to 6. No, it's they're either more than 6 and all the moments go away. I should say reaction moments go away. And then if there's less or 6 or fewer and there's moments, then you leave the moments on there. And you can solve for those moments and see if any of them are equal to 0 there. Any questions about that? Okay, so those moments just, they go away because we're perfectly rigid, and since it's perfectly rigid, and remember, perfectly rigid means that my yardstick does not do this. Perfectly rigid means that no matter how hard I push, it always keeps the same shape. But as soon as I have, if I don't have another support reaction, I need to carry a moment right here. But as soon as I get another support reaction, I no longer need to resist moment as long as this is perfectly rigid here. So I see a question here. 6 reaction forces at the points where the moment would be, or more than 6 in the whole body? More than 6 in the whole body. So if we go back to our original one up here, we would have a total of 9 unknowns in this whole rigid object. And then so we say, okay, 9 unknowns, that's too many. Now that means all the moments go away. So if you count more than 6, then it's more than 6. If it's 6, then it's okay. We can leave the moments in there. And let's change this to all the reaction moments go away. Okay, on Wednesday, we'll look at now, okay, how do we start solving this? For example, this problem right here. This is on the supplementary example problems. Take a look at this if you want. We're not going to work this one. We'll work a different one on Wednesday. But basically, we're looking for the XYZ components of the reaction at the fixed base of the pole. Our first step, just like in 2D, is to draw the FBD. Now that we're in 3D, it's going to be a lot of moment stuff. And a lot of vectors. And so using R cross F again, and also we'll lay out a course map, or not a course map, we'll lay out like a map of all the unknowns and what equations we have and what equations we're going to use first in this one. But you can see, right, now we're in 3D, we're going to have vector stuff going on, and we're going to have to be able to solve problems with up to 6 unknowns. So we'll go ahead and stop there for today, even though we started a little bit finishing up some stuff from last time. Still, we're able to finish ahead of time. You all have a great rest of your Monday. We'll see you on Wednesday.